wait for it to load. All right, so I'm Scott Lowe, and this presentation really is for anybody that's interested in the driving technologies behind modern mission operation systems. I am the lead architect on Meridian, and every day I'm working with Linux and container technology. And container technology is what we use to build Meridian, which is our solution, as Brian and others have explained during this presentation. Meridian is our solution for creating modern reusable flight dynamic ground systems. And it turns out that containers are really excellent technology to build server architectures in general, but more specifically, they're really great at building modern space mission operation systems. So I thought it'd be a great thing to talk about today, and really just wanted to go through how we put together an entire flight dynamics ground system using container technology. So for context, if you've seen any of the other presentations on Meridian, you're probably well aware of its capabilities, but it's a fully featured flight dynamics suite. It's got a web-based front end that allows an operator to perform virtually any flight dynamics task, and it's powered by FreeFlyer, which is our incredibly powerful and flexible astrodynamics engine. Instead of talking about what Meridian does, though, what we're going to be talking about and taking a look at is how it works using containers, which are incredibly powerful. So take this use case as an example. Imagine that you're a system administrator and you're handed the Meridian deployment package file, which contains everything that you need to stand up an instance of Meridian. You run that installer on any server architecture, and within minutes, you have a fully deployed and running flight dynamics ground system. So what traditionally takes several days of server room configuration can happen in a single execution. And I'm serious, it really actually takes about 10 minutes to get everything up and running. So how do containers do this? Well, that's specifically what we're going to talk about a little bit more today. So in a nutshell, we're going to run through how we at AI use containers to build and run Meridian. And we're going to take a look at the conceptual basics of containers. And then we're going to take a look at how containers can be constructed and deployed and combined and orchestrated to create a robust, scalable, easy to deploy, modern flight dynamics ground system. But before we do that, let's take a little step back in time, only a decade or two, so we can see how we would traditionally build a flight dynamics ground system the old-fashioned way. So at AI Solutions, we've been building flight dynamics ground systems for many, many years, and we've developed it for many, many missions. And every time we do, we create the same flight dynamics capabilities, things like orbit propagation, maneuver planning, orbit determination. And after doing this over and over and over again, we gained a lot of experience on how to make this process efficient. And we always start with one thing, which is the flight dynamics engine. So at AI, flight dynamics is what we do, and I think we do it really well. But again, that's something that we've learned how to do over a long period of time. All of our knowledge and skill has been sort of meticulously gathered into our own homegrown flight dynamics engine, which is FreeFlyer. And time again, this is the engine that we use at the center of any of our flight dynamics ground systems. So, excuse me. So when we build our system, we immediately bundle FreeFlyer with a set of scripts and software, which together perform all the flight dynamics tasks that are required on a mission. And as the ground system continues to be deployed, we add additional components and layers, operator interfaces, automation scripts, configuration management. And traditionally, all of these things are custom built to have the various needs and capabilities of our target mission. And so what we end up with here is a very custom tailored solution. It's well built, of course, but it's always complicated and nuanced. And as you can imagine, every addition increases complexity. Mission soon gets to the point where it needs really a dedicated subject matter expert just to understand how all of the pieces work together. And this is the way that things have been done for a long time, but it's really not scalable. You get to a certain point where things get etched in stone and you end up creating a legacy system that's sort of full of small details for things to be missed or things to go wrong. And sort of worse, you end up with a mission that's not repeatable. So every new mission that you create, you have to start from scratch. Every new mission requires a completely new team. And you can't just copy paste your ground system from one mission to another. So after successfully navigating this terrain for years, we as a company decided to take a hard look at these systems. And we wanted to figure out a way to create a generic solution that used modern technology and a way that allowed us to develop a common set of scripts and software that any ground system could leverage to do the astrodynamics that are common across missions. So more than just the flight dynamics, but all of the inner workings in between. We wanted to bundle the infrastructure that goes into building a flight dynamic system so that we could reduce or eliminate all the common and time-consuming system administration tasks in addition to, the regular astrodynamic software. And so, of course, the solution that we came up with was Meridian. So you may have heard this term before. This is what we call flight dynamics in a box. And this is taking a holistic look at building the flight dynamics ecosystem and then packaging it up into something that can be repeatable. And it turns out that this makes it pretty easy to deploy and maintain across different missions with different requirements. And just like a car, we build a common reproducible frame around our engine. We bundle customizable set of microservice components that are common to a ground system with our common flight dynamics engine. And by allowing each mission to choose only the microservices they need, we create a flexible system that can maintain a common standard, but can also be tailored to meet mission requirements rather than reinventing the wheel each time. And this approach also scales really well. So with a single core team, we can actually support hundreds of different missions like this. But taking all of that and packaging it up is a way easier said than done. And ground system, as you know, can consist of so many different interacting components, and managing all these things can really be an overwhelming task. And often you have dedicated teams to doing this. So how do we develop a packaging standard for our microservices that reduces the work to the system administration team and doesn't add, and allows us to support any number of missions? Well, of course, we do that with containers. So containers are basically what allow us to develop and deploy our software in a simple, reusable, well-organized way. So let's talk a little bit more about how we do that and take a look at what a container is really like. Well, simply put, containers are just a way of grouping a process or a piece of software and its environment together. Usually this is a single process like a server application with its configuration, environment, and network settings. This gives us a standard way to create microservices that are completely encapsulated. And it makes system administration simple. A microservice in a container can be installed in any environment with little to no setup. And because the container includes everything the microservice needs, there's no worry. Everything gets deployed exactly as is in the target system. Essentially, this is like wrapping each service or application with its own lightweight operating system, but it's not the whole operating system. In the industry, this is what's called OS level virtualization. Each container has its own custom tailored set of dependencies, such as specific versions of programming language runtimes, system libraries, environment settings. And once a container is built, it can be shipped as an image file to any server that runs containers. So once containers image is available on your server, you can actually instantiate or clone that instance of your microservice. And this essentially guarantees that the environment you build into your container is identical to what's installed on your production system. And the container continues to have its very own ecosystem to work with in that production system. It remains independent of anything else that's on the operating system. And so in a nutshell, again, this is how we package, deploy, install, and run Meridian. Essentially as a set of pre-built and ultimately configurable containers, which gives us the ability to ship as predicted sets. Rather than building custom software for each mission, we deliver custom sets of containers to meet mission-specific requirements. This is known as container orchestration and is what makes container technology so flexible. We're able to build software independently of our deployment environment, and the mission's ground system server can really be configured in any way. We can guarantee that regardless of the configuration, our containers will still be compatible. So this is just like Lego blocks that you can swap between sets and they still work. So the tools these are the tools that we use on Meridian, but what's the software that really facilitates that? Well, that's easy. That's Docker. You could say Docker is the whale in the sea of options because it's the largest and most well-supported container engine in the industry. And the number of options are vast indeed. But Docker is what we use on Meridian because it's well-supported, it's rock solid, and it does an incredible job of making container management easy. And one of its greatest features is its cross-platform capability. So it bridges the gap on different operating systems and allows us to run containers on Linux or Windows or Mac, or really whatever the supporting mission needs. As long as Docker supports it, we can deploy it. So Docker makes it so that despite the differences behind the scenes, a container is run in the exact same way, regardless of its underlying operating system. And really, this means that we can test what we fly and fly what we test. So yeah, let's take a look at Docker in action, just to get an idea. So once again, let's sort of journey back in time to the way things used to be to get a traditional look at a server deployment. So again, traditionally, this is how we'd set up a mission system in a server room. We'd start by purchasing a server hardware, a single computer and a server rack, and we'd install a single operating system on that server, and we configure that server's OS to meet the mission's specific needs. And 10 years ago, this was pretty much the common way of doing things. You have a separate physical server running a single operating system for every different application or a set of applications that you have in your server room. And it would be custom tailored with its own applications and its settings for a very specific purpose. So to make things more flexible, server rooms were made virtualized. And in a virtualized server room, you still have one large server, but it's a much larger server, a larger set of physical hardware, and it's built to support the entire server room. It's installed with a hypervisor, which is an operating system that's designed to support virtual machines. And in this setup, a system admin can create as many virtual machines as they need, each with its own operating system, application, settings, etc. And they can create new virtual machines simply by running a few commands. And this is a fantastic approach in many ways, but it's still somewhat monolithic. An admin is creating and copying entire operating systems. They're still managing things like system dependencies in each operating system, and this can be costly in terms of time and resources. Even machine virtualization doesn't actually solve the problem of configuration management. So let's take a look at that, and let's take a look at what problems can pop up in a traditional software deployment. So in traditional deployment, what you have is a bunch of production files that are generated in a development environment, and sometimes even those files are generated in production themselves, things like compiled code, configuration files, etc. And you make sure that all of those are on the production machine. And many software packages offer installers, but in ground systems, this isn't always the case. And even then, each installer has a different process or procedure, and often its own set of independent system dependencies. So you really have to go through a checklist for every piece of software that you want to install on the system. And even once things are successfully running, maintenance and upgrades are usually problematic, or at the very least costly. So in the end, there's a whole lot of bean counting, checklists, configuration management, and approvals that you have to go through, all to keep that software mission safe. So you can see here in our example, in our development, we're running Python 3.8, but there's no real guarantee that in production we're going to be running Python 2.7, except for, like I said, a checklist where things like human error can creep in. And I'll admit, when I was a young software engineer just breaking into the aerospace world, I was pretty surprised to see some of the maintenance procedures involved. Things like version control, SVN, Git to manage the differences can get complicated pretty quick. And in the end, it always sort of ends up like as a nightmare for your system administrator. And frankly, it's why they get a whole day of appreciation every year. So developers sometimes forget to tell the system admin which versions were updated. Again, human errors can creep into checklists, and even installation scripts can go wrong, and often do. So what's the solution? Well, I think you probably already know, Docker. We use containers to solve the problem of performance overhead, environment isolation, configuration management, all in one go. Containers are like virtual machines, but they're much more lightweight. Whereas a virtual machine splits up the physical hardware into virtual machines, containers split up the operating system kernel into virtualized operating systems, or more technically speaking, virtualized user spaces. Containers typically contain only a single application, which means a container takes up significantly less overall system resources than a virtual machine. They're configured and managed by a system service or daemon known as the container engine. In our case, that's Docker. And the container engine is far less intrusive than a fully blown hypervisor. And altogether, the container ecosystem requires a significantly less resource overhead. So as long as the Docker engine is installed on our server, our containers can be deployed in minutes and instantiated in seconds. So what does deployment look like now that we have a container engine running the show? Well, with Docker, we can organize all of our mission critical processes, files, system settings, environment settings into containers. And organizing our software and environment has a lot of benefits. But the big feature that we can is that now that we can run our containers in any development environment or on production systems. And so example, as you can see in the chart, even though we've built our containers on Windows, we can actually deploy to a Linux-based ground system as well. And by using containers as a standard, we can design system components completely independent of the operational environment. And so deploying with Docker is as simple as bringing that container over from our development environment to our operational environment. And again, doesn't matter what the operational system looks like as long as it's got Docker on it. But building and installing is one thing. So how do containers get from our shop to a mission system? Well, in a cloud-based environment, Docker uses the Docker registry, which is simply a network-enabled repository for Docker images. It's a way of sharing containers. A popular example of this is Docker Hub, which is hosts images publicly. Of course, registries don't need to be public, and they're often hosted within private, secure infrastructure. Just like with many repositories, containers are saved as binary images pushed to the registry where they're versioned, tagged, and stored. And when a system admin wants to install or update a container, they simply put the latest container from the registry or pull the latest container from the registry, and it's up and running on their system. And of course, we all know that ground systems are often built on air-gapped and secured networks. So how do we install without a network? Well, Docker's got us covered again. In the case where a development environment is not on the same network or the registry isn't available, we can save our containers as a simple tar file. The image container file can then be delivered via secure FTP or USB or really any secure system that transports files. On the mission system, system admin simply copies the container image to the system and then loads it into Docker. This mechanism also allows for images to be named and tagged with a version number so that a mission can maintain specific version of containers. This is like configuration management for free. So now that we are taking a look at what Docker gives us, let's compare a typical ground system with one that's running containers. So this is an example of how Meridian would run without containers, a lot like our traditional ground system that we built from scratch. There's a lot of work involved in managing all the files and environment settings and system dependencies and network connections, et cetera, et cetera. And when we built Meridian, we knew that the software itself was only going to be half the battle. Organization and management of all the in-betweens is just as important. So we made the decision right from the start to use Docker. And we know that by bundling each of our server components into its own container cleans things up a lot. But how do we get everything working together? It's not enough to have these containers running in isolation. Our components need to be sharing files and data. And we still need our components to be connected to the network. So to do that, we're going to take a look at another major feature of Docker, and that is Docker Compose. So while Docker handles the running of individual containers, Docker relies on Docker Compose to handle the orchestration of container collections. So Docker Compose gives us the ability to configure the in-between or the network of containers and define rules for how the different systems interact with each other, the host system and external hosts on the network. In each mission, it can be configured with only the containers necessary to support mission tasks and requirements. And the biggest feature, it allows us to define an entire system definition in a single, simple to understand configuration file. And I mean, this is a really powerful concept. It's a single recipe that defines the entire system of systems. So how does it do all this? Well, to get an idea, let's take a look at an example system recipe, aka a Docker Compose file. So each container in a Docker Compose file is defined as a top-level node. In this example, we have a web interface, which is essentially our browser's host, a task processor, which is our free flyer engine, and a database container. And for each container, we have settings that map specifics of that container. So the specific image and the version of the container, the ports, the volumes, which are essentially file shares between the host and container environment or even external hosts, all the ports and networking mapping. And we can even define which containers wait on others before starting up, and sort of a miniature dependency graph. So when we get when we want to get all of this up and running, we essentially take this file and we command Docker to run using this file, and we get the entire Meridian ground system. So that's really the power of Docker. With a single file, we can really stand up an entire ground system at once. And what we get is a running instance of Meridian that looks something like this when it's deployed. Each microservice is packaged with its own internal ecosystem. It's running as configured for the overall ground system. And it's a true separation of concerns. Again, the software doesn't need to be aware of the host, and the host doesn't need to be configured specifically for the software. And deep down here, if you look in this chart, at the heart of Meridian is the task processor, which is our engine component. It includes FreeFlyer to power our astrodynamics capabilities. But how do we create a container-based flight dynamics engine? Well, you'll remember that in a traditional flight dynamics system, we bundle FreeFlyer with a standard set of mission plans, common data, and to get together with the data and the scripts, this engine is used to execute a standard set of tasks. In Meridian, each task is a pre-built mission plan, but we need FreeFlyer to be continually available on our overall system of containers. So how do we do that? We add the Meridian task processor, which is essentially an HTTP server that wraps the FreeFlyer API. So this task processor maintains a set of mission plans and data format standards, and it serves as a connection point to the rest of the Meridian network. And essentially, it allows us to have a continually running web-enabled instance of FreeFlyer. And of course, we pull that all together into Docker, just like we do with all of our other components, and that gives us an encapsulated standard container that is beneficial for all the reasons that we've covered so far. And as you can imagine, this gives us an incredible amount of system configuration stability. We no longer need a complicated setup procedure or script just for our ground system. We just drop this container on the host and you're done. But besides having the engine details tucked neatly away, there's also one other major benefit, which is that our container now works like all the other Meridian containers. Because it's a standard Meridian container, it's interoperable with our microservice ecosystem. And this highlights the true building block nature of containers. And that means that we can easily configure multiple systems for multiple missions without having to change the inner working of our containers. And an operator can interact with Meridian as a single entity rather than a set of microservices in order to run standard mission tasks. From the operator's perspective, they're just running one thing. And this is how we're able to achieve support for such a large number of specific missions using generic components. So let's take a look at things from the top level. Here we have a running instance of Meridian, and as the operator goes about running their flight dynamics tasks, we know that behind the scenes is an orchestration of containers supporting the operation. This operator is running a process that's specific to their mission with all the level of detail required, as if Meridian was written from scratch completely for them. Data flows from the web browser to a web host container, and this web host formats the data and sends it to the data management container, and that stores it persistently and triggers the execution of the astrodynamics engine container. And then once the execution is complete, the results are returned back to the data management container and persisted and then sent back to the web host. And this provides the entire task run right to the operator's web browser. So I hope that helped illuminate container technology and the utility that this technology offers to developers in our field through the example of Meridian. Of course, I love this stuff, so please feel free to reach out to me if you have any questions at all. And thank you very, very much for attending.
First question is, can Meridian run multiple tasks simultaneously? It interacts with FreeFlyer, so how does Meridian, I guess, balance and run multiple instances of FreeFlyer at the same time?
Sure. Meridian runs FreeFlyer in the same way that you would with a desktop-based installation. So, FreeFlyer is connected to a license server that allows you to have pools of licenses or seats available to you at any time. So when a task processor gets a request from the rest of the Meridian ecosystem, it spawns a new instance of FreeFlyer, takes a license, and runs with it.
Awesome. Next up is, does abstracting these into containers slow the processing?
No, it actually is pretty low level. Linux and containers have been, or containers in Linux have been a feature that's been available for a while. This is sort of related to namespaces and C groups in Linux. So it's pretty robust, and containers, as opposed to like a virtualized operating system, are really really bare bones. Really, you're just using some underlying Linux bookkeeping that allows you to separate these containers. Everything really is actually on your computer and your file system, but Linux does a pretty good job of separating these containers out into separate packages without adding any kind of overhead.
Great. Next, are containers created each time a mission plan runs?
In Meridian, no, they are not. They can be. That is something that is perfectly possible with containers. You can think about instantiating a container in the same way that you could instantiate an application. So you can have a server application that's always up and running, or you can have a application that you run 10 instances of. So in Meridian, what we do is we have one server application that's up and running all the time, and we maintain and stays up and running, so it's continuously connected to the network. That's what I'm trying to say. But behind the scenes, it's instantiating sub-processes, child processes within that container's ecosystem. So, you know, if we wanted to, we could switch that out and do a new container each time. And for some scenarios, that's the way to go. So far on Meridian, we haven't run into that scenario yet, but I'd be excited to try it out.